Hello, I'm still Jim Hutchins. This is still Weber State University. It's still the Health Sciences 1110 course, Biomedical Core. What's new here is that today I'm going to be talking about Module 3, the molecular level of organization, which is just our fancy way of saying biochemistry. So that's what we're going to be looking at today is the biological chemical constituents that make up living things, particularly human beings, which we're studying in this course. We'll start off with a series of definitions and the first four objectives. So the first definition that we'll get to is the definition of organic molecules, and it's a very simple one. Organic molecules are those that contain carbon. So to go a little bit beyond that definition, we're going to look at some of the things that we learned in Module 2 that are going to tell us about why carbon is special and why carbon is the basis for life. You probably know this already if you've ever cooked something too much. You take something which was once alive and you cook it too much, and what does it form? It forms carbon. So that tells you right there that carbon is the basis of life. Carbon is able to form molecules that are more complex than inorganic molecules. So remember that in the last module we looked at the ionic bonds in, for example, sodium chloride. Well, there's not too many different ways of putting together sodium atoms and chlorine atoms to make sodium chloride. It's pretty much the same no matter what you do. You always get NaCl. They always donate one electron, pick up one electron, and that's that. In the case of carbon, as we'll see, there's a lot of different ways to put together a carbon-containing molecule. So organic molecules are usually larger than inorganic molecules. The types of molecules that we're going to look at are carbohydrates, lipids, which also include fats, oils, waxes, proteins, nucleic acids, which are used as the genetic code for the cell, but also to tell the cell what proteins need to be made. We'll look at that in modules 4 and 5. And then adenosine triphosphate, which is the energy currency of the cell. And when we look at the objective with adenosine triphosphate, or ATP is the abbreviation, then we'll look at what I mean by energy currency. Remember from Module 2, when we were covering the concept of valence in Module 2, Objective 17, we learned that carbon atoms have 4 electrons in their outer shell. They can either give away those 4 electrons and become like a helium atom and have a completed outer shell that way, or they can pick up 4 electrons and become in their outer shell like a neon atom and have a charge of -4 that way. Either way, carbon makes 4 bonds. Now, if you ever have the pleasure of taking organic chemistry class, you'll notice that somewhere in the front row, maybe the second row, there's some geek with his glasses taped together who's going to watch the professor like a hawk. And every time the professor is drawing a structure that contains carbon on the board, and it's going to be a lot because after all this is an organic chemistry class, so he's drawing these carbon-containing structures up on the board, and the geek is going to at some point stop the professor and say, "Professor, you drew only 3 bonds to that carbon." Or worse, "Professor, you drew 5 bonds to that carbon." And the professor will turn around and look at the board and stare at it for a minute and look at it and say, "Sure enough, I only drew 3 or I drew 5. And that the geek knows and the professor knows that that's impossible because carbon always takes 4 bonds. No matter what we do in terms of giving away electrons or taking electrons, it's always going to make 4 bonds. So the number for carbon is 4. Carbon is always going to make 4 bonds. That's going to be really important for understanding the shorthand that we use for symbolizing carbon-containing molecules, and we'll get to that in just a few objectives. Now, the other thing that comes out of this, carbon making 4 bonds and being able to bond with a wide variety of other compounds, is that carbon forms what are called isomers. Notice here we have a glucose molecule. The molecular formula for glucose is 6 carbons, 12 hydrogens and 6 oxygens, in other words, C6H12O6. But it turns out that the molecular formula for another sugar, a completely different sugar called fructose, is also C6H12O6. How can this be? Well, if we look at the way that these atoms are arranged in this molecule, we'll notice that there's a completely different arrangement of atoms around the 6-carbon backbone, which forms the core of this molecule in each case. But the different functional groups, and we'll learn what a functional group is in the next objective, different functional groups are arranged in a different way around the 6-carbon backbone. So these are called isomers. When two organic chemicals, have the same structural formula, C6H12O6 in this case, but have completely different structures.